Hello everyone. In this section, we're going to talk about the pigeonhole principle. So what is the pigeonhole principle? Think about that you have couple holes in the wall, and then there are three birds that they constantly come to hang out on those holes in the wall. Well, at some point, because there's just two holes in the wall, there must be at least one of the holes that is going to have two at least two of the pigeons or the birds. They can be a combination of like 2 and 1 or 3 and 0. But in one of them, at least you're gonna have more than two. Okay. So in general, the intuition is that if you have n pigeons that are flying in m holes, and you have that n is bigger than m, so you have a higher number of pigeons, then at least one of the holes must contain more than two pigeons. The whole pigeonhole principle is given by the notion that a function from a finite set x to a smaller finite set y cannot be one-to-one. So there must be at least two elements of x with the same image in y. So another example of this is, imagine you have a group of 13 people. At least two of them, they need to share the same birth month. Why? Because, well, we have 13 people and we have 12 months. This relationship is not going to be injective. So if we think of the best scenario, there are 12 people, that one per each month, but then the people number 13, the person number 13 is going to be in one of the repeated months. Same like, let's talk about hair counts in New York City. The New York population is bigger than 8 millions. And the max hairs is less than 300,000. So at least two people, they're going to have the same hair count. Now, let's talk about how to apply it. There's a step method, the step-by-step method that we can check in here. So first, we need to identify what is the pigeons, so the objects that are being assigned. Number two, we are going to identify the pigeonholes, or the categories we're assigning the pigeons. We verify that the number of pigeons is bigger than the number of pigeonholes, and then we can conclude that at least one hole is going to hold more than two pigeons. Let's talk about the birth month example in detail. So we have 13 people. We can classify them as X1, X2 to X13. The pigeonhole are the 12 months, January, February up to December. We can define a function b of xi, where b of xi means the birth month of xi. And the output is going to, given the input of one of the xi, one of the people, then it's going to give me 1 month. Notice that, of course, we have more pigeon than pigeonholes. And so someone has, some month is going to have more than two people. Now, we can generalize this pigeonhole principle. And we can say that for any function f of xy with the cardinality, or the number of elements in x being n, the number of elements in y being m, and a positive integer k, if the multiplication between k and m is less than n, then some y is has bigger than k plus 1 per images. So what this means, generalizing to the idea what we had before, is think about that you have the last initial in a group of 85 people. So we have 85 people. Those are going to be my pigeons. The pigeonholes are going to be the initials. So we have 26 possible initials, which are the letters from A to C. And let's try with a K, let's say 3. 3 times 26 is going to be 78, which is still less than 85. So that K works. That K works for our purposes. So we can say that there is at least 3 plus 1, or 4, people that are going to share the same last initial. Notice that this is a generalization because we're saying more than 2. Okay, this k in the past was 2 because this is the one of the possible numbers that we had on the most basic notion. With k equals 1, then we just have if m is less than n. But now we can just generalize that idea as if we have k multiplying m and that is still less than n, then you can get that is at least k plus 1 more. How to find k will be a good question, and what you want to do is you take the largest integer so that k times m is less than n. Okay, so let's use this as an application for repeating decimals. So the theorem, which is the pigeonhole principle, is that the decimal expansion of any rational number, a over b, either terminates or repeats. So why is this? Well, the long division of a number a by b is going to produce an infinite sequence of remainders, which is r0, r1, r2. And those possible values, those possible remainders can only be between 0 and b minus 1 once again, by the long division. And what we learned before about or arithmetics. The remainder sequence never ends if r of I is different from 0 for all I, but has only b possible values. By the pigeonhole principle, some of the remainders must eventually repeat. So let's say that the remainder for j is equals to the remainder in k for j less than k. But if this repeats, that means that there's going to be a pattern in there. There's going to be a repetition of the decimals. So this means that the decimal digits between position j and k are going to repeat forever. Now, one example of this will be 3 divided 14. That is equals to 0.214285.7, and this is periodic. This number of remainder here is periodic, and the block 214857 is going to repeat indefinitely after this. So this is what we call one periodic representation. So now another application of this will be consider t being the set of the numbers from 1 to 8. Suppose that you have 5 integers chosen from here. Then there must be 2 of those that at least the sum is 9. Why is that? Well, the idea of this is like you partition t into pairs that can add up to 9. So for example, 8 with 1, 2 with 7, 3 with 6, 4 by 5. So the pigeon is you need to choose 5 integers, right? And the idea of the pigeonholes is that we're going to have that is going to land at least in one of these 4 pairs above. If you have 5 integers, you at least going to have couple numbers that are going to land in these brackets. And in particular, this is given by the pigeonhole principle because 5 is bigger than 4. So there's at least 2 chosen integers that must fail on the same pair. And those 2 are going to add up to 9. Now, the hard part, of course, is finding the right partition. But once you do, then the pigeonhole principle is going to apply directly. Okay, so in summary, the pigeonhole principle gives me that if n items goes into m in categories with m less than n, some category is going to have more than 2 items. The function version of this is related to f being from x to y with the number of elements in x being bigger than y. Then it cannot be injective. And for the generalized version of the pigeonhole principle, we have that not only m is less than n, but k times m is less than n. So you can have that some category gets at least k plus 1 items. We have a couple of applications where every rational number has a terminating or repeating decimal expansion. And there are some other applications that you can use to check possible allocations of numbers given a particular sum. Some common mistakes that you want to avoid here is swapping pigeons and pigeonholes. This is the critical part. You need to clearly define which set is matching to which. because it matters which one is larger. And be careful with confusing must exist with always happen. The principle guarantees the existence of the worst case scenario, not that it always happens the same way. You gotta be careful with the k in the generalized version. You need to find the largest k that make it possible. That k times m is less than n, and your conclusion will be that it's bigger than k plus 1, not that k. Okay? Okay, so next, it's very important that you see more examples of this. So make sure that you're checking the practices for this particular concept on the class note examples. But next, we're gonna also go to combinations.